Making and breaking of CC bonds is critical in organic synthesis, and it's critical in metabolism. These bond formation and breakage reactions typically proceed via enolates. In a previous video, I've considered the aldol reaction, in which enolates are formed by deprotonation, remember, of an alpha CH, giving a CC bond and putting the electrons onto the oxygen, where they're at lower potential than the base we started with. Today I'm going to consider what happens when we take the electrophile up one oxidation state. And in that case, we no longer form an alcohol, as in the aldol reaction. We will form a carbonyl. Aldehydes are poor sources of enolates in this reaction because aldehydes are also good electrophiles and they tend to react with themselves. So let's restrict the discussion then to enolates of esters, amides, things in the carboxylic acid oxidation state. Let's take an ester, for instance, deprotonate on the alpha CH, puts the electrons again on the oxygen that was previously the carbonyl. That gives us our nucleophilic enolate, and now we must react it with our higher oxidation state electrophile. That could be an ester, but let's take a simple one, an acid chloride. And let's imagine that the acid chloride is non-enolizable itself, so there can be no complications. The enolate reacts with the acid chloride and the key step happens, formation of a C-C bond. That gives also a tetrahedral intermediate where the electron density is on the oxygen of the electrophile, and then because there's a leaving group on that same carbon, those electrons have an escape route. They come back, they form a CO double bond. That's good. CO double bonds are highly energetic, and a chloride is lost, a very stable leaving group. Note that the product is more acidic than the ester that we started with in this reaction. It's more acidic because the product is a beta keto ester. The CH2 between the ester and the ketone is highly acidic because it's stabilized by both electron withdrawing groups. As the product forms then, it's deprotonated by the base, giving a stabilized enolate, not as reactive as the ester enolate, doesn't usually react further. What do we achieve in these reactions? Well, like any process where we deprotonate alpha to a carbonyl, we take away hydrogen and then react with an electrophile. In other words, add something else. It's a substitution on that carbon. So just to recap then, what's the key difference between this reaction and the aldol reaction? Well, in this reaction, we have a leaving group on the carbonyl. For an ester, that would be an alkoxide. For an acid chloride, it's easy to see that's the chloride anion. For an anhydride, that would be a carboxylate. In the aldol reaction, we don't. We simply have a CH or a CC in the case of a ketone. So there's no easy escape route for this tetrahedral intermediate. The product then of the aldol reaction is an alcohol. The product of the Claisen reaction, as this is called, is a beta keto ester or a beta keto amide, depending on what enolate we started with. To relate this to something really important in human biology, let's consider briefly what happens when we eat food. That food will typically contain some glucose precursors. They are metabolized quickly, and then excess glucose, as we've already discussed in the chapter on carbohydrates, excess glucose is stored as glycogen, but if the intake of glucose exceeds the rate at which glycogen can be produced, then the excess energy is stored as fats. And that's where fatty acid biosynthesis comes into play. In fatty acid biosynthesis, acetyl-CoA serves as the enolate source. That acetyl-CoA enolate will react with a thioester. Sr is a good leaving group. It will form a beta-keto thioester of acetyl-CoA and displace thioxide. That beta-keto thioester is then reduced at the ketone group all the way down to hydrocarbon. This gives a longer fatty acid chain than we started with. And the process can be repeated over and over again. So a very, very simplistic view of metabolism then is we intake food. Any carbohydrates are broken down into monosaccharides like glucose. Glucose is further broken down via retroenolate reactions into smaller and smaller fragments. And ultimately, they give CO2 and water, a lot of ATP. Excess food consumption leads to production of glucose that can't be metabolized instantly. That goes to glucogen, the polysaccharide. Excess intake of food over that is stored for a rainy day as fat. How is that fat produced? By breaking down the glucose into acetyl-CoA. Acetyl-CoA forms effectively enolates, but in enzyme active pockets. And those enolates react with thioesters, so that after reduction of the CO double bond, we can form long-chain fatty acids. Long-chain fatty acids are a very good source of ATP energy. They're in fact a better source of ATP energy than glucose. It's just that they're more slowly burned. Thank you very much for listening. Bye-bye. No problem. I can edit you out.